This is the second part of the 17th lesson in heat transfer. The 17th lesson is focused on developing a qualitative picture of convection heat transfer. This qualitative picture will form the basis on which we will begin to make calculations of what the convection heat transfer coefficient is in a variety of flow situations. In this lesson, we'll be looking at an important dimensionless number in convection heat transfer, the Prandtl number. This number is named after the famous fluid mechanician Ludwig Prandtl. By the end of this lesson, you should be able to recognize the definition of the dimensionless Prandtl number. You should also be able to explain what the role the Prandtl number plays in convection heat transfer. Finally, you should be able to provide representative values of the Prandtl number for gases, oils, and liquid metals. On with the lesson.
So hopefully I've convinced you then that this thermal boundary layer thickness is pretty important. It's really, really important, right? Because the thermal boundary layer thickness and the nature of the flow in the boundary layer are the two most critical things for predicting the temperature gradient. So we need a way of quantifying that, right? And what that's going to show up as is this dimensionless number called the Prandtl number. So the Prandtl number is defined as the ratio of the kinematic viscosity of the fluid to its thermal diffusivity. So this is the kinematic viscosity in the numerator. And this is the thermal diffusivity. In the denominator. I think I've already shown you that the units for the kinematic viscosity are identical to the units for the thermal diffusivity. And there's a reason for that, because they are both kind of linked to the same physics. So because of that, sometimes I even refer to the kinematic viscosity as the momentum diffusivity, because it tells me how quickly momentum diffuses across the streamlines in the laminar boundary layer. So this ratio of these two fluid properties that we call the Prandtl number is going to allow us to say something about the relative thicknesses of the hydrodynamic and thermal boundary layers. So it's going to give me some information about this ratio of these two thicknesses. Does that make sense? When the Prandtl number is big, that means that the hydrodynamic boundary layer is much thicker than the thermal boundary layer. When the Prandtl number is very, very small, it means that the thermal boundary layer is much thicker than the hydrodynamic one. So if you're thinking about, ultimately we're trying to do calculations. In the review, I told you the hydrodynamic boundary layer thickness is tied very closely to the Reynolds number. Okay? So the Reynolds number tells me something about how thick that hydrodynamic boundary layer is. Now, if I layer in this idea that the Prandtl number gives me this relative ratio, right? I can take my hydrodynamic boundary layer thickness and say something about the thermal boundary layer thickness if you tell me what the Prandtl number is. That's why it's important. Does that make sense? So I'm going to give you a chance to write down what I just said and capture this idea that why is the Prandtl number important to us from the perspective of convection heat transfer. So I'm trying to convince you that the thermal boundary layer thickness is really critical. And I reminded you from fluid mechanics, the Reynolds number tells us something about the thickness of the hydrodynamic boundary layer. The Prandtl number is the link from that information to the thermal boundary layer. It's the link between the two. There are basically three kind of broad categories that fluids fall into based off of the values of the Prandtl number. You can see Prandtl numbers around unity. So you have very similar values for the kinematic viscosity and the thermal diffusivity. You can see Prandtl numbers where they're much, much less than unity. And you can see Prandtl numbers that are much, much bigger than unity. So this approximately equal 1 case are all of your gases. Any gas has a Prandtl number basically between 0.65 and 1.2. So in gases, momentum and thermal energy are diffused on similar timescales. So the nature in which those two things move are very similar. Prandtl number much, much less than 1 are liquid metals. Okay, so if you take this logic that I've been trying to convince you of, that we want thin thermal boundary layers for good heat transfer, right? The thinner the thermal boundary layer, the steeper the gradient, the better the convection heat transfer coefficient, right? So liquid metals with the Prandtl number much, much less than 1. That means that the thermal boundary layer is much thicker than the hydrodynamic one, right? Is that good or bad? Do we want thick thermal boundary layers or thin ones? Thin ones, right? So in liquid metals, the thermal boundary layer is a lot thicker. So do you think that means that they're bad heat transfer fluids? What does your intuition say about how good a liquid metal is at transferring thermal energy as a thermal conductor? Good or bad, do you think? Good. Yeah, they're good. So this is kind of backwards. So even though the Prandtl number is really small, they're still really good thermal conductor. They're still really good heat transfer fluid because there's more to the story than just this, right? There's more to the story than just this. What's the other part of convection? We're talking about the advection part. There's also the conduction part, which is the thermal conductivity. So in liquid metals, the high thermal conductivity outweighs the low Prandtl number. And so they're still really, really good heat transfer fluids. So even though their Prandtl number is low and their thermal boundary layers thicken very quickly, they have such a high thermal conductivity that they're still good, right? You still get really big H's. You don't get big H's from the advection part, you get big H's because of the conduction part. Make sense? Your Prandtl number, much, much bigger than 1, are essentially all of your oils. So you should be thinking motor oil, so SAE 5W30, any other glycerol, any other kind of thick, oily type substance typically has a high Prandtl number, which is good from a heat transfer perspective because that means that the thermal boundary layers stay thin. And thin thermal boundary layers are advantageous, okay? It's not the end all be all, but it's advantageous. Okay, any questions on that information?